To pick it up from last time where we left off, we were talking about multidimensional arrays, and I gave you a visualization of what that looks like. 1D arrays are just regular old arrays that we've been looking at so far, where you've got one dimension. But if you've got two dimensions, then you've basically got rows, and then each row has a column. So each row can be seen as an array itself. You can also have 3D arrays, 4D arrays, etc. But we're not going to go up that far. We're only going to stick with 2D arrays at most. In general, if you are thinking about doing 3D arrays or 4D arrays, there might be a better way of doing what you're trying to accomplish. In C, the way that you do this is with an int star star, or if it's a double, if it's a matrix or a table of doubles, then it would be double star star star. The star star is essentially a pointer to an array of pointers, and each one of those pointers then points to an actual row. Once you've got that, then you can use two index variables, the ith row and the jth column, and then you can access individual elements within that array. So what we're going to do is we're going to reproduce that code that I gave you last time because we didn't go over the details of it. But what I'm going to do is I'm going to create a couple of variables here, int n and m. And then we'll assume that these are initialized. In fact, for purposes of the visualization later, I'll just go ahead and make this, say, a 3 by 4 array. In other words, 3 rows and 4 columns. Right? And then I'm going to go ahead and create a matrix out of this. So a matrix with 3 rows, 1, 2, 3, and 4 columns in each row. To do that, I need an integer pointer. An integer pointer pointer. A pointer that points to an array of integer pointers, and then each one of those is going to point to an actual row. I'll go ahead and call it matrix because that's what it is. I'll initialize it to null initially. Right? But what I need to do is I now need to call malloc, matrix is equal to something malloc, right? In order to set this up. Now, I'm going to want an array of pointers here. An array of pointers, one for each row. The first pointer is going to point to the first row. The second pointer is going to point to the second row, etc. So how many pointers are you going to want if you have 3 rows? Well, 1, 2, 3 pointers. But since I put that into a variable, I'll go ahead and have n. Right? Now, how many bytes that an integer pointer takes? Right? How many bytes does an integer pointer take? Does anybody know? 4, maybe? That's a 32-bit system, right? Then this is getting down to addressing and word size and stuff like that. This is where you get the terms. Go way back to the 1980s, where you've got the Nintendo Entertainment System and Genesis or whatever they were, right? What was the original NES system? You play retro games, right? It was 8-bit, right? And then along came the Super Nintendo system, and that was 16-bit. And then 32-bit. And in fact, it used to be that processors on computers were 32-bit. You cannot buy a 32-bit processor anymore. Instead, what do you have? 64-bit, right? So that's kind of referring to the size. That's somewhat referring to the size of a pointer. 64 bits would be 8 bytes. All right. Well, if this is on a system where it was only 4 bytes, if this were way back in the 80s where it was only 1 byte, then it would all be different. How do I make it so that my code, I'm not hard coding this to simply just 8? Right? How many bytes does an integer pointer take? Int star, right? How many bytes does an integer take? Well, size of int. Well, how many bytes does a double take? Size of double. How many bytes does an integer pointer take? Well, what's an integer pointer? It's an int star, right? And you can't, white space doesn't matter, but I do like to put a little bit of white space in there. All right, well, I need to make that pointer that it returns, that chunk of memory that has now been allocated, I need to make that compatible with matrix, which is an int star star. Right? So this is looking very, very familiar. Right? And unfortunately, the code highlighting is not doing all that great here because it's in Markdown. But that's what this is the actual code here. All right, well, this sets me up for, let me go ahead and visualize what this looks like. There we go. Visualize this execution. Hopefully it works. Oops. Null is undeclared. Where is it declared? In the standard library. So we'll go ahead and try that again. All right, there we go. And we can ignore that. All right, what does this visualization look like here? I'm only setting up the array of pointers. So let me go ahead and go through this. There's 3 by 4, 3 and 4. And initially it's equal to null. When I call malloc, that sets up an array of pointers of size 0, 1, 2, of size 3. Now what is each one of these pointers pointing to? Right, well, as the question mark here implies, who knows, right? It's uninitialized pointer. It could be pointing to dead beef. It could be pointing to a memory location that doesn't belong to me. No matter what, I can't treat it. I can't treat it with any the sane interpretation. Okay. So what comes after? I need to initialize the first row, and then the second row, and then the third row. In other words, I need to make this first pointer point to the first row. I need to make the second pointer point to the second row, and I need to be calling malloc to create that row. That suggests a loop for I running from 0 up to, well, how many of them are there? N, I plus plus. I'm going to set up the ith row. Right? The way that I'm going to do that is the way that you already know how to do this. By calling malloc to simply set up a one-dimensional array, because each row is simply a one-dimensional array. So matrix sub I, that's the ith row in the matrix, is going to be equal to int star, right, malloc, a call to malloc, and I'm going to want m integers in that. How many bytes does an integer take? Size of int, right? And this will now set up each row for me. Let me go ahead and take it over here to the visualization, edit this code, and add that last part into it. Okay? And again, we'll see this in action. Let me go ahead and increase the size slightly. Yeah, there we go. All right, I'll go ahead and walk through this. Just as before, the first call to malloc sets up the array of pointers. Each one of these is a pointer that's going to point to a row. On the first iteration, we go through and we've set up our first pointer. Right? It's pointing to the first row after this call to malloc. On the second iteration, I is now 1, and it sets up that first row. And on the third iteration, it sets up the third and final row. Each one has 4 columns because we specified that it was of size m, and m was initialized to 4. Okay? Once this is done, once the loop is done, we've got our 3 by 4 matrix right here. And we can treat it like a matrix. We can treat it like a 2-dimensional array. After that, I'll go ahead and say matrix of 0, 0 is equal to 42, right? Matrix of, what's that, 0, 0, which one is that going to be over here? Which one of these things? So it's going to be the 0th row, so this row right here, the 0th column, so this will end up getting set equal to 42. How do I set the bottom right element to, say, 101? It'd be the 3rd row, so index 2, and then the 4th column, so index 3. So, what was it, 2, 3, I'll set that equal to 101. Okay? Again, if you want to see this visualized, we can edit this code, add this back in, and visualize this execution. With a 2-dimensional array, you need 2 coordinates. You need 2 indices. Let me go ahead and fast forward through this because we've already seen it. There we go. There's our 3 rows. Now I set 0, 0. That's going to set the top left element to 42. And this last one should set the bottom right element to 101. What about the rest of these? What values do they have? What do the question marks mean? Uninitialized, right? It could be anything. It could be 0. It could be dead beef. It could be whatever, right? It could be whatever was stored in that memory location before you got to it, right? So you can't read anything into uninitialized values. So this raises a question. Once you are done with a 2D array, how do you clean up? Right? Well, how did we clean up a one-dimensional array? What function did we use? We freed it up. Right? Let me go back over to this code, edit it. All right, I used it, whatever I wanted to do with it. And let's go ahead and free up the matrix. Right? Let me go ahead and try and see what that looks like. Again, I'll go ahead and fast forward through this all. And fast forward all the way down to line 13, 14. We set it. There we go. What's this going to free? Well, what is matrix pointing to? I've got my pointer here. It's pointing to this array of pointers. So what is that actually going to end up freeing? Just this array right here. What about those three other arrays, this array, and this array? Is that going to be freed up? Nope. I'll go ahead and go forward on this. And what happened? Well, the visualization here means that we don't see it anymore because we don't have any access to it. But was that memory actually freed up? Nope. What did we call that again? What did you see? What did you witness yesterday? You witnessed a memory leak. All that memory is now leaked out. So I don't want to just free up the matrix. Or I want to free up each one of those rows as well, right? So what order should I do that in? Should I free up the rows first? That sounds like a better proposition. All right, so to do this, you need to free up each row first, then the array of pointers. Okay? So how would I go out about doing that in C? Well, how did I create them? With this simple for loop up here. Right? And if you want to clean up, free up the ith row in the matrix, well, then it's just free matrix of I. Remember, that's a pointer because this is an array of pointers. And so it'll end up freeing them at that matrix. Once I'm done with that, now I'm free to free up the array of pointers. Free matrix. All right. Matrix, there we go. Let me go ahead and bring this over to our code visualization. Edit this. And I'll get rid of this and replace it with the proper way of doing this. And again, fast forward. I don't know if I can fast forward to a particular line or not. I can, yeah, there we go. I can just jump forward here. There we go. All right, so I'm about to free up the first row. Now, it doesn't matter if you do the first row, then the second row, the third row, or you work bottom up, the last row, then the second row, then the first row, or if you just do them in random order, although that would be a more difficult code to write and kind of weird to do. But I'll just go ahead and start freeing it up from top to bottom. After this first call, you see that row was freed up. And what is this pointer pointing to? Well, it's pointing up to freed memory locations. If I tried to access the elements in that array, what would end up happening? Undefined behavior, right? It could be a segmentation fault. It could be that the values are still there and you can use them. It could be that another process has already claimed that memory, or my processor has already reclaimed that memory, and it would maybe be a segmentation fault. The next iteration gets rid of the second row. The third iteration gets rid of the last row. I don't know why they're still visualized over here, but the last after those that for loop is done, now I've got poop emojis everywhere. I just need to clean up this one array right here. And when I do that, now it's all cleaned up properly. No memory leaks whatsoever. Okay? All right, great. So if you did this with, now you see why, what if you did this with a three-dimensional array? You'd have, how many loops would you have now? 2 loops, right? And to clean up, another 2 loops. And you'd have to clean up, for each row, for each column, you'd need to clean up that aisle or initialize that aisle. All right, and so it gets really, really complicated really, really fast. And of course, you've got int star star star, and you would have 3 index variables. There's really not a call for that. There are much better solutions if you have n-dimensional, higher dimensional array, need for higher dimensional data like that. Okay. There are some alternatives, ways of doing this. For example, the way that I just did it, I initialized each row by itself. There are other alternative ways that you can do this. For example, you can have an entire big chunk of memory. You can visualize it as one really long array. In this case, it was a 3 by 4 array. So how many elements are there total? 12. I could have instead just created one long one-dimensional array of size 12, and then did my own arithmetic for jumping to the next row, which would be four elements over, and then another 4 elements over. So I could just take this matrix, this square matrix, and I could flatten it out into one dimension if you want to. And that's actually what a lot of people do in actual programming. Another alternative way is visualized in the book and in the videos, where you can create a chunk of memory and then initialize your pointers and just simply point to the first 4 elements over here. The second pointer will point to the next 4 elements. The third pointer will point to the next 4 elements. So you can still treat it like a 2-dimensional array, so you don't have to do your own pointer arithmetic. But the difference there is that instead of initializing 1, 2, 3 rows, you're initializing and calling malloc once to create one big giant chunk of memory. There's really no rhyme or there's really no one way that it should always be done one way or another. It all really depends on the application, but we're not going to get into it that deeply. If you're interested, go ahead and again do the required reading, watch the required videos. That's arrays. At least that's arrays for integers and doubles by extension. Any questions so far? Okay. Because what about arrays of, so what about arrays of chars? Right? What do we call them? Strings, exactly. Right? So what are strings? Strings are simply just ordered sequences of characters. And this is this is not 19. There we go. Yeah, okay, I'll keep it like that. No, I want 3 on this and then 2 on this. There we go. And move this up there. There we go. All right, so strings are simply just ordered sequences of characters. And in other words, in the context of C, again, this is why we cover strings after arrays, because strings are nothing more than arrays. In C, strings are simply just null terminated arrays of characters. Right? In other words, char values. Okay? Now, what do I mean by null terminated? I'll talk about that in just one moment. Right? But before we, I want to draw your attention to something that we covered in the first couple of weeks. Is that in C, all characters are simple ASCII text characters. Right? Some languages have full native Unicode support. For example, Java. If you continue next semester in Computer Science 2, we'll cover Java in the first few weeks, and that has native Unicode support. In other words, you can directly put in CJK fonts, which are Chinese, Japanese, Korean fonts. You can have Cyrillic fonts. You can have emojis, right, and that kind of stuff. And you can support all of those Unicode characters and print them out. You can read them in if people are able to type them somehow. And unfortunately, you can even use them as variable names if you really wanted to, if you set up the Java virtual machine, the Java compiler to handle that. By default, it usually is not set up to do something like that, and you wouldn't want to, because you don't want to go int smiley face is equal to 10, right? That doesn't make all that much sense. But you can code in Unicode as kind of a joke. But in C, C is old school. C is only going to support those ASCII text values. A through Z, capitals, lowercase, 0 through 9, exclamation point in the ASCII, basic ASCII text table. Right? Most languages also provide a robust library to process strings. Right? C included. Right? So where do you think the standard string library is located? What would I have to include? What do you think? String.h, right? All those string functions are in the string library, and we'll talk about several of them, and we'll talk about several of them next week as well, because you don't want this is one area where you don't want to have to reinvent the wheel. If you want to copy one string over to another string, here's a function to do it. If you want to get a substring, here's a function that you can make make it do it for you. The reason that you don't want to do a lot of this work yourself is because it's a lot of just grunt work on arrays, because strings are arrays. They're just simple arrays of characters. In C, let me emphasize this, all strings must be null terminated. Right? So you remember when we first started talking about arrays, I told you, and I emphatically told you, that there is no way to determine the size of an array, right? Some tutorials will incorrectly say that there is, and in certain limited instances you can determine the size of an array, but this is why you have to do your own bookkeeping. If you call malloc and request enough bytes to hold 100 integers, you need to keep track of the fact that this was 100 integers. Because if you want to iterate over it, you need to know that, well, there are only 100 integers in here. Strings are no different. If you create a string array, then you need to keep track of how big it is. But there's a slightly different way of doing that. Here's a string. What we're going to do is we're going to put a special character at the end to indicate that that's the end of the string. Right? That's the null terminating character. Right? The null terminating character is, well, how do I get it? /0. That's not an O. There is no /O. That's the number 0. Right? This has an ASCII text value. What do you think it is? What value do you think it is? It's 0, right? And it is not the same thing, or same thing as the keyword null. That means something different. That's the null pointer. It is not the void, right? Void character. There's no such thing. It essentially has a value of 0, but you don't treat it as 0. It is not the character 0. That would be single characters here. Single characters 0, right? And I'll put this into code mode here. All right, but when it renders, it'll look a lot better. That has some ASCII text value. Does anybody know what it is off the top of their head? ASCII text table. Right? Nope, because the null terminating character is 0. The character 0 is 48, right? 48. That's kind of small, but you can see it right there. Right? So it's not the same thing as any of these other things. So in C, we have a half a dozen ways of saying nothing, right? Void, null, the null terminating character, 0, etc. Right? So the null terminating character is /n. If a string is not null terminated, operations on it may be, again, that boogeyman there, undefined behavior. Right? And it could lead to segmentation fault. It could lead to undefined behavior. It could just be that you're screwing up your own memory. Okay? So let's go ahead and take a look at some examples here, strings in C. All right, again, in C, strings are arrays of character elements. Right? You can declare a string using the familiar syntax. So, for example, if I wanted to create a string of size, say, 10, I could have char. I'll go with message here, right? And let's make it of size. Let's make it of size 10, right? There's an array of characters, right? That's a static array that I showed you that you can do with integers and doubles. So that's very familiar. But here's the caveat. Can it hold a string of 10 characters? Careful. 10 characters. What needs to go at the end? The null terminating character. So at most, how many characters can you hold? 9, right? So only 9. This can only store 9 characters as you need at least the null terminating character at the end. All right? So let me go ahead and initialize this stuff. Message sub 0 is equal to H. Message sub 1 is equal to E. Message sub 2, 3, 4, 2, 3. Hello, right? Lots of typing, lots of copy pasta. Should I be doing this? Right? No, probably not. There's probably a better way of doing this. But before I get rid of my grunt work right here, is this a valid string? Careful. Hello. If that's all I want in my message, hello, then what do I need to put at the end? The null terminating character. How do I get the null terminating character? \0. Right? So what I want to do is I want to visualize this. I'm kind of interested to see how the visualization tool will actually look at this. Let's get rid of all this stuff. There we go. Hopefully it'll look like what I want it to look like. Yep, good. It is showing you that it's an array of size 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In other words, it's of size 10. The array is of size 10, but you cannot hold at most 9 valid characters because you always need at least one of them for the null terminating character. Let me go ahead and walk forward in this, and you can see that it sets it HELLO, and then we've got a null terminating character. What about those other 4 characters? Well, they're valid. I could use them if I wanted to, but I'm not. A string can be shorter than the array that holds it, and that's perfectly valid, and that's perfectly fine. If you create an integer array of size 100 and you only use the first 10 of them, right, you can do that, right? There's nothing preventing you from doing that. But it's kind of inefficient in a way because I am wasting these 4 bytes over here. 4 bytes is nothing nowadays. But also, again, that's a terrible way of initializing stuff. Do you want to initialize a string where you have to manually set every single character? No. So there's a much better way of doing this. Char message, right, of 10 is equal to, and I can put in a string. Right? And this is what you've been doing this entire time with these are called static strings, where you've got double quotes, and then you can put as many characters as you want in there. The compiler is smart enough to see, okay, well, you have 5 characters there, and I'll put the null terminating character in there for you automatically. Compilers are dumb, but at least they can do some of that grunt work for us. So that's going to result in the same exact thing. Right? And let me go ahead and show you that it does. I'll edit this code, take out all that grunt work stuff, and put that in, and you can see that it'll result in the same thing. That it'll automatically put that null terminating character in there for me. Come on, there we go. In fact, it put null terminating characters everywhere else for me. There's no guarantee on that, by the way. This is the only one that was guaranteed to be there. So that you would have valid string, valid string, valid string. That's the end of the string. If you're going to do any processing of this string, that's where you stop. It's a big flag of this is the end of the string. Go no further, because I can't guarantee you what the contents of it are. I can't even guarantee you that that memory belongs to you. Okay? Well, there was no need to waste those last 4 bytes, right? So I could have done it like this instead. Message. You remember the 50-cent word that I gave you? That I don't have to provide the size of the array if I'm initializing it right away. Making something shorter. Jeet, right? Did you eat? That's elision, right? So you don't have to specify that it's 10 bytes or of size 10. You can just go ahead and let the compiler do the counting for you, right? And in this case, before I hit visualization, how big of an array will it allocate for me? HELLO, just 5? 6, why? Because of that null terminating character that it puts in there automatically for me. 0, 1, 2, 3, 4, 5, that's 6 characters right there. Right? So great. It takes care of all my work for me, and I don't have to worry about it. That's how you can create strings and initialize them in one stroke. Now, strings in C strings are mutable. Right? What does mutable mean? Mutable, mutate. What does mutate mean? To change, right? So if something is mutable, mutatable, right, then it's changeable. That is, the contents of a string, just like any array, can be changed. Right? So for example, let me go ahead and go into this mode. So char name, I'll go ahead and use my name here, CHRS. Right? Now this creates an array of size 5, again 6. Right? There's some gotchas there. But I left my first initial lowercase. Let's go ahead and change that. Names of whatever is equal to capital C instead. Note the difference. Double quotes for strings, single quotes for single characters. If you're setting only one character in the array, then you need to use single quotes. Now, which character do I need to change to C? 0, right? The first one. What if I tried to do something like this? Names of 0, 1, 2, 3, 4, 5 is equal to T, and then names of 6 is equal to CHRISTO. I have to remember how to spell my own name. 7, Christopher. Okay, you get the idea. I'm going to go ahead and create my entire first name here. All right? So you can change a single character, but careful. Is this valid? Valid. There we go. Well, let me try it. Let me see what happens in my code visualization. Again, I'm kind of curious. I don't know how it'll handle this. All right, visualize this. And I'm not going to do my full name, right? So there we go. There's Chris. I'm changing that first one. You see the first one was changed to capital C. What's going to happen if I change names of 5 to T? What happens to that null terminating character that tells my program that that's the end of the string? There. Is there any end of the string anymore? I have no idea. It depends on, does that memory belong to me? Keep going. And the visualization doesn't even show that I'm accessing memory that's outside of this array. What happens if you access memory outside of an array? Segmentation fault, undefined behavior. Maybe you're just screwing up your own memory over here, right? So you have to be careful, right? In general, overwriting past a string past the null terminator can lead to undefined behavior. Right? However, you can always make a string shorter. So let me take that same example, but I'll work it in reverse. Let's say go char name, my full name, Christopher. There we go. How can I just change it into my shortened name, my nickname here? Names of something is equal to, I can go ahead and set the null terminator character somewhere else there. Where could I set it so that it's just Chris? Now you all know my name, right? If you didn't know it before. Right? CHRIS. I want to change this lowercase t to the null terminating character. Right? What should I? Which index should I set? 5. Right? Now I'm going to visualize this, but I also want to print this out. Printf %. Now here's a good question, and some people have already been using it. What's a good placeholder to print an entire string in printf? S. Print a string. Right? Let me go ahead and do that here and here. And I'll show you that it indeed is Christopher the first time I do this. But after I've shortened it by cutting the string off, right, then it will print just Chris instead. Let's see this in action. It's prints, come on. It prints Christopher up there. OK, great. And then it will set that t to a null terminating character. Now, it didn't destroy that memory. It didn't clean up that memory. that memory is still there. You can still see that I have OPHER over here, as well as the null terminating character over here. I didn't change any of that stuff. But as far as C is concerned, you've shortened up the string by cutting it off early. And you can see that it's just Chris after I do this. Right? So you can always put as many null terminating characters as you want in the string. In fact, you can put a null terminating character at the beginning. That leads to an empty string, a string of length 0. Yeah?
Would we need to include our string.h in order to do all this?
No. Nothing that I've done so far requires the string library yet. Printf, that's in the standard input-output library, and it can handle %s. Right? Good. All right. So I'll cut and paste that. Come on. I'll cut and paste that so you have it in the notes there. And what was it again? 5. Right? So making a string shorter by placing a null terminator is usually valid. It doesn't shorten the size of the array. It only shortens the string. As far as a C is concerned on what a string actually is. Okay. All right. Well, that's one way of doing this stuff. Everything that I've done up to this point has been a static string. Remember, where static arrays are allocated on the stack, right? I lost my visualization, but again, you can see that string, because of the way that I declared it, it's allocated on the stack right here. Well, what's the alternative? Dynamic strings, which would be allocated on the heap, right? And generally, you want to do that so that you're not abusing the stack space. Right? So, dynamic strings. You can always use malloc to create a char array dynamically. So how would we go about doing that? Here's my goal. Create an array that is able to hold 100 characters. Right? Or create a string that's able to hold 100 characters. So I'll go ahead and put that into a variable n here. And then I'll go ahead and create, my really long name, Christopher Michael James Burke, and I think that'll. I do have 2 middle names, and I'll be able to hold all of those names together, as well as the spaces, as well as doctor in front, and I don't have any suffixes, but I can make one up or something. All right, char star call to malloc. How many bytes do you need? N times. How many bytes does a character take? Well, 1 technically, but should you do that? Probably shouldn't. You should use the same stuff that we've been using up to this point. Size of, well, what are you trying to allocate? You're trying to allocate characters. Now, the question here is, does that actually achieve my goal? Did I create an array? I created an array of size 100. I'll give you that. But is it able to hold on 100 characters? No. How many characters is it able to hold at most? 99. So one common way of dealing with strings is always to simply just add 1. Right? And now that holds 100 characters with an extra character to accommodate the null terminating character. Right? Now what I'd really like to do is I'd like to set this equal to my name. Christopher Michael James Burke. There we go. Let's see if I'm allowed to do this. Let's bring it over here. In fact, I'm going to do this in REPL because I'm not sure that it's going to generate a warning. Include stdlib.h. There we go. Try to run it. It's still going. While I'm doing that, I'll go ahead and write some code here to print out my name. I guess no, it didn't do anything, right? It was perfectly fine doing that. But let's think on this a little bit more. What is this actually doing? It's creating a dynamically allocated array. Where is that located? on the heap. And then then I've got name is a pointer. As of line 8, it's pointing to something over in the heap. Now on line 9, I'm creating a static string right here using double quotes, which is allocated on the stack. So line 9 is actually taking this pointer that's pointing to one thing and simply just making it point to something else. Let me visualize this for you. Get rid of that. All right, come on. All right. And go forward, forward. So 100. And then we've got this really, really long array over here that's allocated on the heap. It's a dynamically allocated string. Okay. Now let's go forward to the 11th line. Did you see what happened there? Right. Let's go back. Is that the same array? Nope. In fact, I can prove it to you. Let me edit this code again. And what I'll do is I'll say names of, I don't know, 50 is equal to f. There we go. Because I have no f's in my name. So visualize this execution. Somewhere way down at the end, there should still be an f. If these were the same strings, then there should still be that f in there, right? I'm assuming that all my names don't have more than 50 characters, right? Oops, let's go back a step. So where's the f? Oh, did I not do it? OK, I need to go one more step. There we go. All right, there. Now over here, now you see that f at character 50, right? Go one more, and do you even see character 50 anymore? No, it's a completely different array. What have I done? I created something on the heap, and I'm pointing to it. Then I create another static string. It's not visualizing it on the stack. I don't know why. But it should be allocated on the stack somewhere. It's actually somewhere deep down below along with the program code. And I'm taking this pointer that's pointing to something over there, and I'm simply making it point to something else. What happened to that thing over there? It was a dynamically allocated chunk of memory. What happens when you lose your pointer to that thing? It leaks out. I've got a memory leak here. So this will work. The above works in the sense that it'll get what you want, but it is a memory leak. Right? The original array is lost. Right? The assignment operator cannot be used on strings after initialization. It can be used during initialization. The assignment operator can be used on strings during initialization at declaration, right? Just like we did above, right? But after initialization, after you've already created this thing, you can't do something like this, right? Instead, you need a function to copy one string to another string. Right? I want to copy CHRIST dot 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 dot. I want to copy that string into my name somehow. Okay. Now I could write this function myself, right? I could say, all right, well, here's my full name, and this is a string. String full, or not string, char. There we go. I want to copy full name into name. I want to copy one string into another string. So you could do this with, a simple while loop, for loop. Int I equals 0, 0. I is less than something, I plus plus, right? And then what I'll do is I'll say names of I is equal to full names of I. That looks like it's copying stuff, just like we did with copying an integer array into another integer array. What's the problem here? How do I know when to stop? Well, I could go through CHRI 1, 2, 3, 4, 5, 6. I'm not going to do that, right? That's stupid. I need a way to tell how copy C, copy H, copy R. When do I stop copying? When you hit the null terminating character. So maybe instead of a for loop here, I'll design a while loop. Int I is equal to 0. While I'm copying full name sub I is not equal to the null terminating character, continue going. Right? Copy over that character and then increment your I. Right? And I'll go ahead and print out name here and full name. Oops, what's wrong? Oh, there we go. Opening bracket. Okay. And then I'll print out name. It's uninitialized up here, and then I'm copying each one of these characters in full name, which is Christopher Michael James Burke, all over to name over here. Right? So let me go ahead and run this and see if it works. Okay, it worked. Darn it. I was hoping that it's still undefined behavior. Why? I was hoping that it would crash, but it didn't. Why? What's wrong? What happened? Yeah, I copied over CHRIS to blah, 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 blah. I copied. Did I copy that null terminating character right here? No, I broke out of that loop when I did that. So what I need to do is I need to make sure that that last one, name sub I, is equal to the null terminating character. Right? Now, why didn't I have to? Why did I still use I here? Well, I incremented it. It's still in scope, right? It's whatever value is over here, and I'll show you what I mean by printf %d, or I is equal to %d and the line I. I'll show you that it retained its value after the end of the loop. It was still 32. So I'm copying the 33rd character, which is the null terminating character, into the index 32, which is the null terminating character, right? So again, if you're dynamically allocating stuff, you always have to remember that null terminating character. If you are copying over a string, you always need to make sure that your strings, or you're manipulating strings, or you're processing strings, you need to make sure that that null terminating character is in there. Some of the library functions do it for you. Some of them don't. The only way that you'll know for sure is by RTMing, read the documentation, read the manual. Right? But this is how you can copy one string into another. In fact, this looks so useful that maybe I would want to put this into my own function and use it, but let's not. Right? So see, instead, there is a convenient method. The string library provides a convenient method called, well, if you want to copy one string into another, you would do a string copy, or CPY, strcpy. str is the standard abbreviation for string in the string library, and if you can save one character, 40 years ago you did it, so CPY, we're going to do that, right? If you try to, arguably they could have made it shorter. CP is the copy command on the command line. C, well, now it's too short. Now, what does that stand for? That's ambiguous. So CPY is what they've used, right? Let me look that up. Let me RTM, strcpy. And let's, this is a C++ reference, but it's the exact same thing. So how does it work? It takes two characters. It takes a destination and a source. Right? Don't worry about the return value. Why is the destination first and the source second? You're copying the source into the destination. Does that bring to mind anything? Int x is equal to 10. What are you doing? You're taking 10 and you're putting it into the variable x. It follows the same pattern. The second argument is going to be operated on and put into the first argument, just like the assignment operator. But you cannot use the assignment operator for strings after initialization. So we instead have to use this, this function right here. Right? One other thing that I want to bring to your attention is this one is a char star. The destination is a char star. And the source is a const char star. What's the difference there? Const. What does the keyword const do? It gives a guarantee, a promise, that you're not going to change the source because you're just copying the source into the destination. Why would you go mucking with this string over here? Right? It's a read-only string. The read-only string is being copied into this string that you can write to. Right? You can make changes to destination. Why? Well, because there's no const over here. Right? It's advertising the fact that the absence of the const keyword is just as meaningful as its placement there, because it's saying it's probably going to change. Right? And in fact, it will be changing. Okay? Let me go ahead and copy that signature over so that we have it. Right? There we go. strcpy copies the string in the second argument into the first, just like how the assignment operator works. Right? The second argument has a const in front, so it will not make changes to it. But of course, you were copying it into the first one, so the first one will, of course, be changed. Right? Now, here's another caveat here. In fact, let me go back to the documentation and see if it tells us. Copies the C string pointed to by source into the array pointed to by destination, including the null terminating character. You don't get that from the signature. You only get that from the documentation. The documentation is telling you, don't worry about the null terminating character. I'll take care of it for you. And stopping at that point. Right? So it takes care of the null terminating character for you. Beware. strcpy assumes that the source string is valid. Right? That is, it already has a null terminating character. Right? If it doesn't, then undefined behavior. How do you think it works? It works exactly it actually probably uses a memcopy or something more sophisticated, but it works basically like this. It keeps copying, copy, until it sees that null terminating character. Then it stops, just like our while loop, provides the inserts the null terminating character for you. If there was no null terminating character in the original string, it would just keep going. It would keep going. It's a while loop. It'll keep going until it sees that null terminating character. And if there was no null terminating character, it'll just keep going past your array until it finds a 0 byte, at which point then it'll stop. It'll be copying a whole bunch of garbage along with your actual string. The last thing to be aware of, beware, strcpy assumes that the destination string is big enough to hold what you are copying. Right? And what I mean by that is, let's go ahead and let's just try to use some static arrays here. Char name is equal to Christopher. There we go. Oops, sorry. There we go. All right. Let me go ahead and copy that into another copy that's only like, say, 5 characters. Right? strcpy into the copy my name. Is that going to work? Am I going to be able to copy this entire long string here of 12 characters or whatever it is into this array that can only hold, review, how many characters can this actually hold? 4, because that last one needs the null terminating character. So am I going to be able to copy all of this? No, I'd only ever be able to copy at most CHRI, right? But how is it going to behave? Let's find out. Right? It'll probably be fine, actually, because, again, it's a bunch of static stuff. Oh, and where is it? Include. Now I need the string library. Right? And it's perfectly fine and happy with that because I'm not actually doing anything with it. And I'm just overwriting my own memory. I'm just corrupting my own memory now. Right? In fact, I corrupted whatever memory this copy was. I copied beyond it. Again, I wonder what the visualization would do with this. We need a visualization tool for bad code where it visualizes like blowing up or something. All right? There's name. There's copy, much smaller. Christopher is put into a name. A copy is uninitialized. But when I call strcpy, there. Is this null terminated? No. All of this is copied, including that null terminating character. But does that array exist? No. I've overwritten whatever memory was actually here. Right? I've probably corrupted my own memory somehow. And it's not showing up here. In fact, if I continue, it'll probably print just like a REPL did. Yeah, it's happy and fine printing that out because I only screwed up my own memory. Right? But if I were screwing up somebody else's memory, then this would probably result in a segmentation fault of some sort. Okay? So you have to be careful. Again, this is memory management. You have to make sure that whatever you're copying from and into is valid, null terminated, and the destination is big enough to hold whatever you're trying to do. Okay? Yeah?
So anytime we want to change the value of a dynamically made string,
You're calling
static one, and then put the static one into the dynamic?
No. Yeah. Good question. Do we always have to create another array if I want to just copy a static string? No. What you can do, in fact, I'll write out the full code here. Let me go ahead and take this and fix it. What's the proper way of doing this now? Proper way. So dynamically allocate however much space you need, and then strcpy into name, and then you can provide the static string just right there. Right? You don't need to save it off into an array. You can just, the second argument can be just a static string. Now it will be allocated somewhere in your program memory, and if you want access to it, then fine, you need to go ahead and put it into a named array, but you can do it this way as well. Okay? All right. What about determining the length of a string? And this is the last thing we'll do today. So often you want to determine how big a string is. For example, if you want to copy string A to string B, you need to make sure string B is big enough. Right? So thus, you need to know how big the string A is. Right? If I want to copy string A into string B, I need to make sure that B is big enough to accommodate it. So I need a way to determine how big a string is. Right? Let me go back over here to REPL with my full name, Christopher Michael James Burke. Don't ask me why I have 4. But I thought that was long, but no. Some grad students in our department have like 8 names, right? And 3 or 4 different systems think that each a different one or a different variation on it is the last name, so you never know who the heck you're talking about. But let me. So we need to determine how big this is. Int length, right, equals what? What is the length of the string? When we say what's the size of a string, we're talking about the length. How many characters does it have? Right. So I'm going to start this at 0. What's a good way that I could say, well, I could go ahead, this is just a static example. I could say 1, 2, 3, 4, 5, 6. I could do it manually. But let's just assume that I don't have that, right? That I'm given a string instead. How would you go about doing it? C, 1, H, R, I, S, ... When would you stop this counting? 6, 7, 8. When you hit the null terminating character. So probably the same while loop that I had before. While name of I is not equal to the null terminating character, and now I'll need my I. Right? So int I, where should I start it? 0. Right? I will increment I, plus plus. But also, what else will I increment? My length. Right? Now, if you wanted to, you could collapse these. I don't really need 2 variables that have the exact same value. Well, yeah, let's just do length. Let's simplify, man. There we go. Printf. The length is equal to %d and the line length. Right. Let me run this and see what comes up. 32. I think that was the value that we got before, right? When I set the last value to the null terminating character, I think it was at index 33. Let's just make sure by shortening this string up, and I definitely know the answer to that. How many characters are in there? 5. Right. Okay, it works. Except for what? CHRIS, 5 characters. What about that last one? the null terminating character, we generally don't count that as part of the string. That's the special flag value that tells you that that's the end of the string. So 5 is a perfectly fine answer. Understanding that, well, if I'm going to copy this string to another location, I'm actually going to have to, again, add 1 to it to accommodate that null terminating character. Again, this seems so useful. Maybe there's something for something that will do this for me, right? But that's how it works, right? Here's our manual solution. Is going to be this stuff, right? Except that it's not necessary. The string library provides a function to determine the length of a string. What do you think it's called? str, right? Short for string, and len, right? Not length, because that's too long, right? We've got to make sure to use abbreviations because bytes count money. All right, right? 40 years ago, bytes mattered. So it's strlen. It returns an integer representing the number of characters, not including the null terminating character, just like our solution did. CHRAS, there were only 5 characters in there. It's not counting that null terminating character in there. Okay? Yep, and it reacts dynamically to changes in a string, right? So in other words, it only counts up to the first null terminating character. And what I mean by that is, let me go back to the example in REPL, and I'll go ahead and put in my full name, Christopher, right? And if I were to, let me go ahead and run the str, so int length is equal to strlen. I'll ask how big this string is. I won't use my manual solution here. And then I'll ask the same question after I change the string. Names of, I think it was 5 that we were playing around with. I'll set that equal to the null terminating character. I'm cutting Christopher down to just CHRAS, right? The first time that this prints, it'll print like 12. I think there are 12 characters in my first name. The second time that it prints, it'll print only those 5, right? Oh, 11, sorry. 12 including the null terminating. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, yes. All right. Just a sanity check there. 11 characters here, but I changed it. I made it shorter by putting in a null terminating character. This strlen function only counts up to that first null terminating character, and then it stops. It does not tell you how big the actual array is. The actual array here is of size 12. Because why doesn't it tell you the actual size of the array? Because there is no way for you to do so, right? I can't emphasize that enough. There is no way in C to determine how big an array is, right? In general, right? In any interoperable manner, okay? Okay. So, yeah, we've got enough time. Let's do one exercise. Right. So what we've been looking at so far, like string copy, string length, only copies one string into another. Right? It assumes it's the destination is big enough. Right? So let's write our own deep copy string copy function. Right? That is a function that copies one string into another, but also dynamically allocates enough memory for it. Right? This goes back to a question on Monday where we wrote our own array copy, deep copy array, where I copied one array to another array, also dynamically allocated. And then somebody asked, well, that seems so useful. Is there already something to do that for us? And yes, the answer was there's mem copy. But again, it still assumes that you've already created that memory. We're going to do the same thing for strings here. Okay? I'll go over to REPL here and do it. All right. First of all, give me a name for this function. What should you call it? Should I just call it copy? Well, that's kind of generic. What are you copying? strings, right? And here I'm not paying by the character, so I'll go ahead, instead of abbreviating it like this, I'll go ahead and do it fully. Copy string. Except that it's strcpy, that's already string copy. This is something different. This is a deep copy. Right? So I'll call it what it is, deep copy string or deep string copy. That sounds a little bit better. Right? Okay. Well, what does it need to take as an argument here? It needs to take a string, right? And a string is a char star str. Now, a couple of things here. Are you going to be making changes to this string? Probably not. You're just taking the string, creating memory over here, and then copying that string over. All right, why would you make changes to this if you're just making a copy? Right? So to prevent that, we can put const in front of it. Now, when we were doing this with the deep copy of the integer array, we also needed to pass in the size. With a string, do we need to pass in the size? No. In fact, we don't want to because the size could be 50, but the actual string that we want to copy is only 10. Right? And we have a function to do that for us, strlen. Okay? So this function creates a new string and copies the given string into it, returning the new string. So how do I return a new string? Can I do that? Well, the red line tells me no. There are no string. In a lot of programming languages, strings are what are called first-class citizens. First-class citizens are things that exist in the language itself. For example, in C, first-class citizens include integers, int, double, char, float. Right? All the built-in types, those are first-class citizens. But a string, which is an array of characters, is not a first-class citizen here. Right? Because it's something that, well, you have to have a character array. And a character array is just one way to model a string. Right? And so if we're going to return a string, we're returning a pointer to a character array. Right? So what should this look like? What's the first thing I need to do? I need to allocate memory for this new string. Char copy is equal to a call to malloc. Well, I need to make sure that the typecast matches, so char star. How many bytes do you want? Size of char, right? That gives you the number of bytes per character, times how many characters are in this string. strlen of the string. Right? Now, is that correct? CHRAS 5. Do I need an array of size 5, or do I need an array of size 6? So what do I need to do? +1. And make sure that that's in, make sure that that's in the parentheses. A lot of times I'll see people just do a +1 over here, and it'll end up working. Why? Well, because in C, a character is only 1 byte. So you're getting away with it. But you shouldn't get away with it. You should do your proper math here and put that into parentheses. The number of bytes that a character takes times this entire thing. That's big enough. Now, how do I copy this string into the copy? str, cpy, copy string, or str. All right, so create memory, copy everything over. Am I done? Nope. Well, it all works, right? Let me go ahead and create a char name Christopher and char name copy, char star copy is equal to, what did I call my function? Deep copy string of name, and then I'll print them out, printf %s and the line, the original name, the copy, undo, copy, and see if this works. Oh, well, first of all, there was a warning generated. What's that warning? That warning should be enough to tell you what I still have to do here. Reaches the end of a non-void function without returning anything. What did I need to do? Return copy. All right? And now when I do that, it'll actually work, and I'll have 2 Christophers there. What I'll do is I'll show you that this is a true deep copy. I will change the copy of or I'll change the original. Name, so 5 is equal to the null terminating character. I'm shortening that out to just Chris. So it'll be Christopher, Christopher. I'm changing name so that it'll only be Chris, but the copy is a completely separate memory address. So it will be unaffected, and you'll have the same value there. Okay? Questions so far on that? Otherwise, again, the difference between a shallow copy and a deep copy is that a shallow copy, you have 2 pointers pointing to the same thing. A deep copy, you have 2 pointers pointing to 2 different memory addresses. So that changes to one do not affect the other. But with a shallow copy, you're changing the same array, right? And that's not what you want. Right? So keep that in mind, shallow versus deep copies. And I will go ahead and make sure that this is in the notes. Otherwise, you'll have more practice, of course, next week. And tomorrow you'll get more practice with arrays.